This is integration by substitution. I've borrowed this technique from Wiley Plus. It's actually a very old technique, and today I'm going to give it a review. So today we want to talk about integration by substitution. The big idea is this is the anti-chain rule. This is the technique where all x must become w. We're trying to trade our integral in x for an integral in w. And so to make that happen, all the x's have to be replaced with an expression in w, and this includes the dx. So what we're looking for is something to be the inside and then something to be the derivative of the inside. So if we have an integral, we're looking at an integral, and then the outside function is the thing that we're actually going to integrate. So I've been writing that just as f prime to make it look like the result of a chain rule. And then inside, the thing that we're actually integrating is some function g of x. That's the inside. Then on the outside, we have to find the derivative of the inside. And that's getting attached to the dx. So the technique goes, we set w equal the inside, and then we take the derivative of the inside to see what the dw is going to be. So if w is gx, then dw is g prime of x, and this is where we attach the dx. So the g prime of x is there to make substitution go. Once we identify the things that we need, we're going to be integrating f prime of w, and then the g prime of x, dx all becomes dw. So now we have a simpler integral to deal with. The idea is that the g prime of x is only there to make the substitution, happen. It's only there to be the derivative of the inside. All right, so once we have it down to an integral in w, then we can actually integrate. And we get f of w plus c. So we have integrated things. We've added one to the exponent divided by the new exponent. We've done the integral of sine or the integral of e to the x, whatever it happens to be. And so that's why the integral goes and the dw go away, and we have a plus c because we have integrated. And then finally, we go back to our original variable. There's our process for substitution. The big idea is identifying what we need to be the derivative of the inside. So the big idea is that we talked about on Friday. We needed to identify what the inside is, and then also identify what we need to be the derivative of the inside, what we need to make the substitution go, what's going to be the dx. So for example, if I have a function that says e to the 5t squared, we see that we have t, we want to identify what the inside function is. I'm just going to write down what I'm going to need. We want to decide if an integral is an integration by substitution. So we identify something that can be a candidate for the inside function. So in this case, 5t squared looks like it's inside an e to the x function. Just this part, looking at this part right here, it looks like 5t squared is the inside. And it looks like the 5t squared has been plugged into an e to the x function, or in this case, an e to the t function. Now, if we're going to identify, so this is just our first impression, if we're going to identify the inside as 5t squared, I need the derivative of that as a factor. The derivative of 5t squared is 10t. So I need some multiple of 10t, and I have that right here. So identify t as the derivative of the inside. That's going to be the dw. That's where we're going to get the dw. That's going to make this work. So I just need a constant multiple of the derivative of the inside. So let's look at the maneuver that we make. The details of the substitution are to say that w is equal to 5t squared. Then we take the derivative of what we declared as the inside, dw is 10t dt. Now this is not exactly what we have. We have a t times dt. So we don't have 10t dt, we've got 1/10 of that. But we're only off by a constant, so I can rewrite this and say 1/10 of dw is a t dt. We'll look at an alternate formulation for this, where we solve for the dt. I'm not really a fan of the solve for the dt. It makes it too mechanical, but it might be what makes the process click for you. So my strategy is to look at this t and identify it. I only need this t to be the derivative of the inside. It's going to become part of the dw because all x must become w. So now it looks like what we're integrating. T and the dt, t dt is all going to become 1/10 of a dw. And I like to put my constants out in front. What I'm integrating is an e to the w function. So my outside function is an e to the x function. And so we're integrating e to the 5t squared, which is w. And then the rest of the t dt is the 1/10 dw. And so now I've traded all of my t for w. Now we integrate in terms of w. The integral of 1/10 of e to the w is 1/10 of e to the w. This is why we like integrating these functions. We got to remember to put the plus c on, because when we differentiate a constant, we get 0, so we're losing some information. We got to kind of put that back, at least a placeholder, until we find some more information about the particular antiderivative we might be looking for. And then finally, we replace our w with our original variable, in this case, t. So we get 1/10 e to the 5t squared plus c. So we are not just running blind here. We don't have to resort to looking at the back of the book to try to find if we're right. If we take the derivative of what we got, we should get back to the beginning. We can take the derivative to check. So we can check by finding the derivative. Sorry for the sniffles. It's that time of year when all the plants are like, oh, hey, all those people with allergies, let's attack them right now. All the plants, and they're reproducing. So let's take the derivative with respect to t of 1/10 e to the 5t squared plus c. I'm going to need parentheses. The derivative of an e to the 5t squared is got a 1/10. That's the constant. The derivative of e to the something is e to that thing times the derivative of that thing. And then the 10s cancel. We have t e to the 5t squared, and that's what we were trying to integrate in the first place. So it worked. Any questions? So Your job when you first start integrating by substitution is to identify the inside, identify the derivative of the inside, and any constants where you need to make an adjustment. So identify the inside, the derivative of the inside, and then make your derivative of the inside match what you actually have in your integral. So the questions that you're going to have when you're looking at these problems: where did the dt go? Other questions are going to be, where did the 1/10 come from? So those are the two most common questions that are going to happen. The dt is always getting replaced with, is always getting attached to the derivative of the inside that you've identified previously, and that's all absorbed into some constant times the dw. So that's where the dt is always going to go. The 1/10, there's usually going to be some constant out here, and that comes from making this adjustment to make the t dt equal to a 1/10 dw, because a dw on its own is 10t dt. So we're off by a factor of 10 because I've got a 1 in front of my t and not a 10 in front of the t. Any questions? Let's look at an alternate way of doing things. This is another way to figure out what the 1/10 should be. And it's a little more mechanical, and I'm not really a fan of it, but you'll see it out there on some videos out on the internet. So, oops, I spelled E wrong. Hey, saved it. Now, the thinking you cannot get away from. You can't mechanize this so that you're not even paying attention, except by doing tons of problems so that you can start seeing things everywhere. So this thinking still has to go. You identify w is equal to 5t squared. You still have to take the derivative, figure out what the derivative of the inside needs to be. So the dw is 10t dt. So your alternate form, so your alternate mechanics is to solve this part, this second part, the dw, solve for dt. And so dt is going to be dw over 10t. And then just replace that and hope all the rest of the t's cancel. It's kind of the way. That's disparaging this particular technique, which is not really fair. So we still have this t. We have e to the 5t squared. I can replace that with w. Oh, but not in green. That just ruined everything. There we go. And then replace the dt with dw over 10t. And then recognize that the two t's will cancel out. And then from there on out, it's the same. So just solve for the dt and replace it in your expression. The thing that you have to remember here is that you can't just assume that the t's are going to cancel out. You have to see all those t cancel out before you proceed. Before you integrate your integral w, all the t have to become w. So it's on you to make that happen. Sometimes we start, one of the reasons that I don't really like this particular method is that we'll just tend to start assuming that this is going to happen and proceed with an incorrect integral. Well, there'll be too much t going on and we'll just throw it out. This is because for the most part, we're trained to mechanize our math processes, just do mechanics. But when we do just mechanics, we start seeing things and we start making expectations about what's going to happen. So rather than reading things carefully, we just kind of gloss over things, just like when we're reading the printed word. Usually when we're reading some kind of story and it's all or something written in our native language at least, we're not actually looking at all what's going on. We're just glossing over all the numbers. We're just glossing over all the words as a collective and not looking at the individual spellings of things. Let me look at an example of what I mean. I'm going to modify what we just looked at very slightly. So let's suppose that we have an integral of t squared e to the 5t squared dt. The only technique we have right now is integration by substitution. So we're going to check to see if this is a substitution problem. The only candidate for an inside function is a 5t squared. The derivative of the inside is something times t, and I don't have that. I have too much of it. One of these t's can serve as my dw, but what am I going to do with the other one? And if we just try to mechanize our way out of it, it causes more problems than it's worth. Once again, the thinking is all still the same. We're saying the inside function is 5t squared. If the inside is 5t squared, that means the outside function, the thing that we're actually going to be integrating, is an e to the x function, or e to the t. We're going to be integrating e to the w. The name of the variable is not important. To make the inside 5t squared go, that tells us that we need some multiple of 10t. So inside of 5t squared means we need a constant multiple. That's the important word there. We need a constant multiple of 10t to be the dw. Once we identify 5t squared as our inside function, so we can integrate an e to the w function, that says we need a constant multiple of 10t to be the dw. We don't have a constant multiple of 10t or t. We have a constant multiple of t squared. Only one of these t's is necessary to be the dw along with the dt. We have an extra factor of t that we can't account for in our method. So this integrand has an extra factor of t. So we only need one factor of t, but we have two. That's going to keep us from doing substitution. We would have to do something else. I can't turn an e to the 5t squared into an e to the w without an extra factor of t to serve as the dw. This also doesn't work if we just try to mechanize the process. If we set up w is 5t squared, just like before, we'd have dw is 10t dt. If we try to solve this for dt, we get dw over 10t. And what's going to happen is that only one of these t's will cancel out because we only need one factor of t to be the dw. So our integral of t squared e to the 5t squared dt, having dealt with the t squared, 5t squared can be w. And then the dt I replace with dw over 10t. So what happens here is that only one of the t cancels out. Only one factor of t cancels out, so we cannot proceed with substitution. We'd need to deal with that extra factor of t. In some situations, we can go back to our original and solve for t and replace that in, but that will not get us anything in this case. So this is not a substitution problem. We were not able to successfully change all the t into the w. We were unable to trade all t for w. We were unable to trade all t for w.
Are there problems where there are multiple variables of t and you can substitute it, or this is just one specific case where you can't?
This one you can't. So there could be that instead of, if we didn't have a t squared, but if we, for example, had a t cubed, then we would be able to substitute our way into a different integral. Because if we have t cubed on the outside, one of those t can be the dw, and my original substitution, our original substitution, is a relationship between t squared and w. So I'd be able to replace t squared with a factor of w. That would give us an integral that we currently don't know how to do, but it is a substitution that would work. So excellent question. And that makes me decide that I want to do this. We're not going to know how to integrate the one that comes up, but it will be a good indication of making substitution actually work. If I have t cubed out here, if we make the substitution, w equals 5t squared. So if we make the substitution, w is equal to 5t squared, that requires that dw be a factor of t. One of these factors of t. So this says that 1/10 of a dw is t dt. So this takes care of one of those factors of t, but there's still two left over. So if we read this integral, there's a t squared times a t, times e to the 5t squared dt. One of the factors of t is going to be the dw. Since I still have two left, I can replace the other two based on our original substitution. So if w is equal to 5t squared, then t squared on its own is equal to 1/5 of a w. So the relationship still holds. W is t squared, so t squared is also w. So once I've written it this way, one of these t's is going to, factors of t will be the dw, one factor of t for the dw, it's actually going to be a 10th t dw as long, once we include this dt, and then the other two can be replaced by w. And this is based on our original substitution. So that t squared on its own will be replaced with a 1/5 w. So the t squared on its own will be replaced with a 1/5 w. The t and the dt get replaced with a 1/10 dw. So the t and the dt all that gets replaced with a 1/10 dw. E is the function that's outside, that's what we're actually integrating, and the 5t squared all becomes w. So what we're actually integrating here is, I'm going to pull all this out, a 1/50th integral of we to the w dw. Now, we don't actually know how to do this integral that resulted from our substitution, but the substitution worked. All the t were able to be replaced by w. So right now, we don't know how to do this particular integral, but the substitution worked. We don't know this new integral. But the substitution worked. U-T-I-O-N, worked.
Do we cover this in Calc 2, or is that once we get into Calc 3?
We'll cover this week.
Cool.
This one happens to be integration by parts.
Oh, got it. Cool. Thank you.
Any questions?
Does that mean on this one that anything more than t to the third or cubed, whatever, wouldn't work? Because then it would be too many t's?
It depends. So notice that the substitution that we're making to fix this t to the third, I have two t's will make a 1/5 of a w. So if I had t to the fourth, then I would have three of them, and that's not the relation I have. I'd be starting to introduce radicals, and that makes the integration worse. But if I had, say, a t to the fifth, then this t to the fourth, I separate out one of the t's to be the dw. That's the maneuver that we want to make sure that we get in this process. We have t cubed. One of those t's needs to be the dw. Separate that one out. The other ones have to become w's. And it looks like, based on our original substitution, they have to become w's in pairs. So if I had a t to the fourth, or sorry, if I started off with a t to the fifth, then t to the fourth could become a square of a 1/5 w, so 1/25 w squared. But if I started off with t to the fourth, I'd have to convert three t's, and that would be a w to the 1.5. Having radicals in this construction becomes a problem that we'll see when we get to integration by parts. Not a problem that we can't deal with, just not a problem that we can easily deal with parts. And we can't really make the substitution work in a nice way. But these are all good thoughts to have. We know that everything works out just fine if I have, looks like I need one factor of t to be the dw. And then if I have even powers of t left over, I can replace those with w's. So t to the third, fifth, seventh, ninth, that's all good. The ones in the middle, not so much. The most important thing that we recognize is that when we make this substitution, when we decide on this 5t squared, one of these factors of t has to be the dw. And then the rest of them we have to convert in some fashion to make the substitution go. I've also implied that when we get down to this integral here, we're going to want to look for integer powers of w. Any questions? All right. Tomorrow, we're going to look at the anti-product rule, which is called integration by parts. So take a look at section 7.2. The nice thing about parts is that there's a formula for parts. The terrible thing about integration by parts is that there's a formula for integration by parts. You won't have to memorize this formula, but you will have to remember it, and remember it forever. That's not true. You won't have to remember it forever. Once you get out of Calc 2, you can kind of let it go.
Cool. Thanks, Professor.
All right. That's going to be it for today. I'll see you all on tomorrow, and thanks for playing.